Hey, so I'm about to go over the classwork, but I first wanted to just remind you that you do have access to the formula chart and the tables that you'll need. And this will be important for not only this assignment today or this classwork in this week, but also for your AP exam. You're going to want to have access to those. If you have a printer at home, you're welcome to print them, but at the very least, just know where they are so that you can open them and use them during your AP exam when you take it. So where you would find that, it's linked on the AP Stat website under More. There's a formula chart and there's tables, so make sure you have those ready. So this is number one of the classwork for this week. So number one says a medical researcher surveyed a large group of men and women about whether they take medicine as prescribed. So we have this table, men and women, and then we have never, sometimes, and always for if they take their medicine as prescribed, and then we have totals. Notice that these are giving us percentages as opposed to like numbers of people, but we can still follow the same general rules when we find probabilities. So on part A, we're finding three different probabilities. Part one of part A, what is the probability that the person selected will be someone whose response is never and who is a woman? So this would be probability of never and woman. Pen is being weird now and it wasn't being weird earlier, but whatever. So for that one, you have a table, you always want to look in the table as opposed to trying to use your rules, and that was kind of the hint I gave you. So I'm just going to look in my table. Women and never is right here. So 0.0636 out of 1, which is 0.0636. What you don't want to do here is just assume that I would multiply probability of never times probability of woman. It might work, but if you're doing that, you're assuming that being a woman and never taking your medicine are independent, which we don't actually know that for sure. So unless you've tested first to see if they're independent, which hint is what part B is asking us to figure out, it's easier, honestly, to just look at the table. Part 2 of part A says what is the probability that the person selected will be someone whose response is never or who is a woman. So our or is basically, I'm going to write this out first. So probability of never. So our general rule for or is we add, right? Probability of never is 0.12 and our probability of a woman in the sample is 0.53. But if we just leave it there, these 6.36% of people who are both a woman and answered never are being counted twice. They're part of both of these totals. So in order to get my true or, I need to subtract those people. And that would give me 0.5864. And then part 3 of part A says what is the probability that the person selected will be someone whose response is never given that the person is a woman. So we would do probability of never given woman. So for that one, again, I'm just going to use the table. I feel like that's easier. So given woman basically means I only care about this row of the table. So I'm only looking at women, and given that they're a woman, we want the probability that they said never. So we would say this 0.0636 out of this 0.53. So that is part A. Part B is saying for the people surveyed are the events of being a person whose response is never and being a woman independent. So our test for independence is, does the probability of A equal the probability of A given B? And if that does happen, if that is equal, then they are independent. So for this one, I could find, does the probability of someone answering never equal the probability that they answered never given they're a woman? So probability of never given woman is something we've already done in part 3 of part A. And so we already know that that's 0.12, and I wouldn't need to show the work again because I already showed it in part A. And then I can look at my table and see that the probability of never overall is 0.12 out of 1 or 0.12. So those are equal. So yes, they are independent because probability of never is equal to probability of never given woman. And in other words, being a woman does not have any kind of impact on whether or not they answered never. There are other ways that you could show that. You could show, does the probability of woman equal probability of woman given never? And then part C, assume that in a large population, the probability that a person will always take medicine as prescribed is 0.54. So if 5 people are selected at random from a population, what is the probability that at least 4 will always take medicine as prescribed? So this is a binomial. I gave you that hint on the worksheet. So we know it's binomial because I know the probability of something happening once or just in general, and I'm asking what is the probability that it happens a specific number of times. We also know it's binomial because we have a set number of trials. We're talking about 5 people. It's a good idea on something, if you notice that something is binomial, to kind of define it as such. So I'm going to say binomial, n equals 5, p equals 0.54. X would basically be the number who said always. Then I'm finding what is the probability that X, the number of people who said always out of the 5, is at least, meaning greater than or equal to 4. So in this case, we only have 5 people. That's basically what's the probability that 4 of them said it, plus the probability that 5 of them said it. We had talked about in our learning binomial that for a greater than or equal to, usually we would do a 1 minus, so you could also do it that way. You could do this as 1 minus the probability that X is less than or equal to 3. But like I said, in this case, greater than or equal to 4 out of 5 people would just be 4 or 5. Then we would write out the formula is we have 5 choose 4, so 5 people total choose 4 people saying it, times probability of success. So in this case, probability of saying always is 0.54 to the 4th, because we want 4 people to do that. And then probability of failure, so 1 minus that, to the n minus k. So 4 people said always, which means 1 person didn't. And then same idea for 5. So that would be our formula. Now actually calculating that probability. So this is me going through the calculator steps of calculating this binomial probability. College Board has already come out and said, and I say this in future examples today, but they've already said that you will not need a graphing calculator to answer any questions. So probably any binomial questions will focus on formula writing as opposed to calculating. So I'm going to skip through this, but if you really want to know, you can ask me. So number 2 is the one about the fat quarters. If you do any kind of sewing, you know what that is. It basically tells you rectangles of fabric created by cutting a yard of fabric into 4 pieces. So we have the number of defects on the top row, and then on the bottom row we have probabilities. So it says if a fat quarter has more than 2 defects, it cannot be sold and is discarded. So let the random variable y represent the number of defects on a fat quarter that can be sold. So on part A, we are asked to create a probability distribution for y. So y is just looking at the number of ones that can be sold, which is basically 0 or 1 or 2, because if it has more than 2 defects, it cannot be sold. So I'm really only looking at this section, but because these probabilities don't add up to 1, we would have to refigure out the probabilities to put into our table. So it's just kind of finding some conditional probabilities. So I'm going to first set up my table. I'm going to put on the top row 0 or 1 or 2 because those are the number that can be sold. I'll put y over here. Probably could have had another column. And this is probability. And then we're going to find the probability of 0 or 1 or 2 given that we're talking about at most 2. First thing I would want to do is figure out what is the total probability that it would be 0 or 1 or 2. So I'm going to add together 0.58 plus 0.23 plus 0.11. Which is 0.92. So 92% of the fat quarters can be sold. So when we find these new probabilities, I'm going to say, well, what's the probability that it's 0 given that it's 0, 1, or 2? So I would do right here 0.58 divided by 0.92. So what is 58% out of 92%? So I'm going to use my calculator and figure that out, as well as figure out the other 2. So that would be my probability distribution for the variable y. Side note, in terms of grading, if you at least identify or drew a table realizing that you need to only be looking at 0, 1, and 2, but your bottom row probabilities were incorrect, you would still get at least partial credit. So just keep that in mind. Never leave things blank. Always put something. So if you have some of an idea of what you should do, then you can do that. So then on part B, it's wanting us to find the mean and standard deviation of y. So on my formula chart, the formulas I would be using for that would be this probability distribution discrete random variable. So our mean is the sum of x times p, and then that's my standard deviation formula. So I'm going to use those formulas. So my mean or expected value would be basically each number times its probability, and then that ends up being 0.49. It's more important this year than ever that you are showing your work. because they're not going to ask you questions that you need a calculator to answer. It will be stuff that you can do either on paper or show work for. So showing work is incredibly important on this year's AP exam. Which also means that in this case, they probably wouldn't ask for standard deviation, or they might ask for standard deviation having already given you the mean and then ask you to like show the formula for it. So my formula, we're going to take each value minus the mean squared times the probability. And then a little side note calculator trick. Oh, actually, you know what? I'm not going to show you the calculator trick. So that is part B. And then part C is asking, so it says the mean and standard deviation of the number of defects for company G are 0.4 and 0.66. So they give us the mean and standard deviation to start with. Fat quarters sell for $5 each, but are discounted by $1.50 for each defect. So I could write an equation for the price. It's $5 minus 1.5 times the number of defects. So that's kind of my general algebraic equation. That was my hint on this classwork, was to think of an algebraic equation. If I remember my rules for mean, this is kind of like we're doing some multiplication, which is scaling, and then we're doing some shifting. So for the mean or expected value does exactly what we would expect. So if I just plug in the mean, I should get my mean price. $4.40. Always put a unit on things that have units. And then for standard deviation of the price, this is where we have to remember that standard deviation is not affected by shifting. So the 5 part right here would not be affected by it. It is affected by scaling, but keep in mind that standard deviation should never be negative. It should always be positive. So I'm only going to do 1.5 times the standard deviation for the number of defects, which is 0.99. And then the other thing I wanted to mention for part B and part C in the scoring, if you got both your numbers correct or even showed all of your work, but you didn't label which one was the mean and which one was the standard deviation, you would get partial credit. So it's really important to label your things and to put units. All right, so this is number 3. So number 3 tells us the men's shirt sizes are determined by their neck sizes, apparently, because nothing else matters in your shirt size besides your neck size. Suppose that men's neck sizes are approximately normally distributed with mean 15.7 and standard deviation 0.7, so that tells us we're probably going to use a normal model in this. Retailer sells men's shirts in small, medium, large, extra large, and we have kind of our indications of what makes each size. So A says, because the retailer only stocks sizes listed above, what proportion of customers will find that the retailer does not carry any shirts in their size? So I'm going to start by drawing a normal model for our neck size distribution. On this particular part, on part A, that was not a requirement to get the full credit, but to me it's visually helpful. So my mean is 15.7, and then anybody who has a neck size below 14 is not going to have a shirt in their size, so below 14. But also anybody who has a neck size above 18, because extra large only goes up to 18, is not going to have a shirt in their size. So that's the probability we're finding, below 14 and above 18. So what I would be doing is finding both of those probabilities and then adding them together. Now how I do that goes to z-scores. So I'm going to find a z-score for 14, and then I'll find a z-score for 18. So now I've found their z-scores, and as a side note, because this year's test, I've mentioned in previous questions today, would not require you to have a calculator. Now both of these could be done using a simple 4-function calculator, but chances are if there's a question like this on there, they're going to make these numbers easy enough to where that's something you could easily do on a piece of paper. So you probably have some kind of nicer numbers to work with compared to what we have here. So now that I've found those z-scores, I'm now going to go to my z-table to find these probabilities. So we want below 14, so I'm going to go look up that z-score on my z-table. So 0.0075. And then I'm going to look up 3.29, which would tell me the probability less than 18, which is 0.9995. So remember, that's the probability of men that have neck sizes less than 18, but we wanted more than, so I am going to do 1 minus that. So the probability of someone having a neck size less than 14 inches is 0.0075. Probability that a man would have a neck size over 18 is 0.0005. To get the overall portion of people who don't have shirts in their size, we're going to add those two together, which is 0.008. So 0.8% of men will not find a shirt in their size, which is not bad. So part B says using a sketch of a normal curve, so they want you to draw it this time, that is part of the points, illustrate the probability or proportion of men whose shirt size is medium, and then calculate that. So medium, it says up here, is between 15 and 16. So the next thing would be to actually calculate it. I need to find both of those z-scores. And then my trick for between, the way I do between is I'm kind of thinking of it as if I do my z table for less than 16, that gives me all of this area below that. But I don't want that whole area, I just want the in-between. So by going back and finding my z table probability for less than 15, I'm taking out anything that's less than 15. Right, and then what I'm left with is that in-between thing. So that's what I'm going to be doing on my z-table. So I'm going to go look up my probability for 0.43 and for -1. And then I'm going to subtract them. 50.77% of men would request a medium or have a medium shirt size. So then on part C, it says of 12 randomly selected customers, what is the probability that exactly 4 will request a size medium? So this is binomial again. We have a set trial size, and we want to find the probability that a certain number will do a certain thing. We know the probability of just overall someone having a size medium, and we want to know the probability that a certain number will have a size medium. So this is where error carries forward. So for example, if you miscalculated part B probability, but then you use that probability to determine this, you could still get potentially full credit on part C. So with that in mind, if you get stuck on part B and you can't even figure out what to do, don't leave it blank. At the very least, make up a number. You're going to get incorrect on part B, but then you can use that number in part C and you're not completely stuck. So never leave something blank, especially if you're going to have to use that answer in a future question. And then I'm going to define X as basically just the number of medium shirt sizes. So my probability that I'm finding is the probability that X, the number of mediums, is equal to 4. What I'm going to do is look at my formula chart for the formula for binomial probability. So if X has a binomial distribution, this is our probability formula to get a certain number of successes. So again, on this test, you are not going to necessarily be calculating this formula or this answer because you would definitely need a calculator for that, and the test is not going to put anything that you would need a calculator on, especially a graphing calculator, which means at the very least on a binomial question you would have to write out the formula in some way. So knowing your formula is really important on this test. So my formula for binomial probability, and this is exactly, so I will only have to write this formula once on this problem, yay. So I have total sample size, choose the number that I want. So 12, choose 4. And then it's the probability of success, which in this case is 0.5077. To the 4th, so I want 4 people to request medium. But if 4 people are requesting medium, that means 8 people out of the 12 are not. So I have to put that on there too. And on a binomial question, this is as far as they potentially ask you to go. So I'm not even going to worry about reminding you how to do that in the calculator. So number 4, we're talking about the spin the pointer game. So it says a donation is required to play the game, and then for each $2 donation, this player spins the wheel and receives the amount of money indicated in the sector. The spinner has an equal probability of landing in each of the 10 sectors. And then A says let X represent the net contribution to the charity when one person plays the game once, and complete the table. So what we have to realize is that someone is donating $2 to play the game, and then they get the amount of money on the pointer back where their pointer or spinner lands. So for example, if they land on 10, they paid $2, but now they're getting $10 back. So their contribution to the charity is actually -8, right? Because they are actually getting money from the charity as opposed to giving at that point. So the options here are $2 or $1 or -8, because they could land on 0 and get nothing back, so the whole $2 goes to the charity. They could land on 1 and get $1 back, so $1 goes to the charity. Or they could land on 10 and get $10, meaning that -8 goes to the charity. So to figure out the probabilities, I'm going to look for $2. That would be if they get nothing back. So I'm going to look at how many times 0 happens. So 1, 2, 3, 4, 5, 6. So 6 out of 10 is 0.6. For $1, that would mean they land on $1. So we have 1, 2, 3 ones. So 3 out of 10 is 0.3. And then to give -8, they would have to land on 10, and there's only one of those. So 1 out of 10 is 0.1. You really don't need to show work for a question like this. The math is pretty simple, but you had to have the probabilities correctly to get that. Part B is asking for expected value or mean. So that goes back to, this is our discrete probability formula. Cool. So I'm going to write that out and find what that is. So on average per game, they're expecting about 70 cents to be given to the charity. Just so you know, in this question, A and B were scored together. So it was kind of like you had to get the correct probabilities up here and the correct expected value down here. If you got one of those correct, you would get partial. So part C, the charity would like to receive a net contribution of $500. What is the fewest number of times the games must be played? That's real simple. We know we're getting approximately 70 cents per game times the number of games, and we want that to be at least $500. And then this is where, to get full credit, you have to realize that we cannot play a game 714.3 times, and 714 times would not give us quite $500. So to get the full points for this part, you had to round to an appropriate 715 times. So then on part D, it says based on last year's event, it'll be played 1,000 times. Charity would like to know the probability of obtaining a net contribution of at least $500 in 1,000 plays. They went ahead and gave you the mean and standard deviation for 1,000 plays of the game, so $700 and $92.79. We're going to use the normal model to approximate that probability. 0.9846. So the probability that they would make at least $500 in 1,000 plays of the game is 0.9846. So it's a pretty good chance that they will get the money that they need if 1,000 plays of the game are done. So number 5 says a company manufactures model rockets. Once an igniter is used to launch a rocket, it cannot be reused. Sometimes it fails to operate correctly and it doesn't launch. The company estimates that the overall failure rate, defined as a percentage of igniters that fail to operate correctly, is 15%. So it kind of gives us an example of a test. A new igniter called the super igniter with the intent of lowering the failure rate. To test the performance of the super igniter, engineer uses the following process. One super igniter is selected at random and used in a rocket. If the rocket launches, another super igniter is selected at random and used in a rocket. And step 2 is repeated until the process stops. When a super igniter fails to operate correctly, or 32 super igniters have successfully launched rockets, whichever comes first. Assume that the super igniter failures are independent. So on part A, if the failure rate of the super igniters is 15%, just like the original igniters, what is the probability that the first 30 super igniters selected successfully launch rockets? So we have probability of it failing to ignite, we're assuming, is 15%, which means the probability of not failing would be 1 minus 15%, or 1 minus 0.15, which is 0.85. And then we want that to happen 30 times, so the probability of 30 not failing is 0.85 to the 30th power, which is 0.0076. So that is part A. And then part B is saying, given that the first 30 igniters successfully launch rockets, what is the probability that the first failure occurs on the 31st or the 32nd superigniter tested if the failure rate really truly is 15%? One thing that I didn't mention on part A that's also going to apply in part B is that they did tell us to assume that the superigniter failures are independent, meaning that the probability that one superigniter fails or doesn't fail has no impact on the next superigniter failing or not failing. So that is allowing us to keep that 15% or 85% the same for each trial because we know that they shouldn't be affecting each other. Each launch or each rocket is independent of the next. That first part kind of doesn't matter because the first 30 launching successfully are not going to affect the probability that the 31st and the 32nd launch successfully. So really, I can almost kind of ignore that part of the sentence completely. So what I'm really doing is finding what's the probability that the first failure occurs on the next launch or on the one after that. And remember, the process stops after a failure. So probability that it happens on the 31st or the next launch is basically 0.15. And then the probability that it happens not on the 31st and on the 32nd would basically be that it doesn't happen on the 31st and it does happen on the 32nd. So 0.15, and then this one comes out to be 0.1275. And so the total probability that the failure occurs either on the next one, the 31st one, or not on the first one and on the 32nd one is going to be those two added together. So this one, in theory, is a little bit simpler than maybe you were trying to make it, or than it seemed at first. So 0.2775. So in part C, it's saying, given that the first 30 superigniters successfully launch rockets, is it reasonable to believe the failure rate of the superigniters is less than 15%? So I'm kind of going to go back up here and see that the probability of the first 30 launching successfully, if the true failure rate were actually 15%, is 0.0076. And that is very unlikely. And that may lead us to believe that maybe that 15% failure rate is not actually true. And since it was so unlikely to get that many successes in a row, in this case, this kind of gives us good evidence that the failure rate is probably not as high as 15%. So I'm going to type something like that. So that is my answer to part C, and that is number 5. So that's it for today's lesson. There's a lot more numbers and less wordiness in this one. I know probability is typically a section that more people have trouble with, so make sure you are asking me questions and getting clarity on things this week as you go through your classwork and your homework. All right, bye guys.